very excited.
All right, I think we should get started. 306, that's fine, right? 306, that's fine. So let me just give Amitava a very brief introduction for those people who don't know. Amitava is a professor in Princeton's Astrophysical Sciences Department and Princeton Plasma Physics Laboratory. So he kind of straddles what I would call the artificial line between plasma physics from fusion confinement and space physics and astrophysics, including things like large-scale dynamo, dusty plasmas, reconnection, and turbulence. So, like I said, straddling that artificial line that we like to draw in the sand between these two areas in science. So Amitava has pretty much won most of the awards that you can name. But I would say most recently, some of the most impressive awards is the James Clerk Maxwell Plasma Prize for his seminal theoretical investigations on a wide range of plasma processes. So if you look at Amitava's CV, it will take you a couple of days to actually read it in completion, and it's very, very impressive. So we're very lucky to have him here at CITA. And today he's going to talk to us about some of his beautiful work on fast reconnection. And for those people in Plasma Astro here at CITA, we know all about fast reconnection. We use it, it's our basic building block for pretty much all of our theories for doing all kinds of different things. So I mean, this is very exciting for us. We get to have one of the pioneers of the theory sitting with us right now. And that's all I really have to say. I'll keep it short. Thanks so much, Amitava. Take it away.
Thank you, James, for that overtly generous introduction. What a setup. I can only go down. It's really a pleasure to be here. And my last visit to CITA was decades ago when Philip Kronberg was here. And the way I was introduced to Philip was my postdoctoral mentor was Marshall Rosenbluth, who was a close friend of Sterling Colgate's, who was a good friend of Kronberg. So we got to know each other, and as you know, Philip was very excited about black holes and everything to do with black holes, including the magnetization of the universe. He ascribed to black holes. So I was working on the dynamo problem with James, and so we had a common meeting ground. I remember that time very fondly. It was somewhere in between when Scott Tremaine and Richard Bond were trading places as senior director. I'm not exactly sure about the year or time, but they were both here at the time. I even saw, I think, Peter Goldreich. Somebody I learned a lot from dimension turbulence. That was decades ago. So when I came back this time, I got lost in the physics building. 5 minutes from beautiful Massey House to here, and then 15 minutes trying to find out what CITA was. Finally, I had a really good time. So I just want you to know it's really wonderful to return to CITA. I've had the pleasure of spending quite a bit of today with many of you, and I've learned a lot already. You're an exciting group. If I were beginning my life over again, I'd want to be here. So it's really fun to be here. What I'm going to talk to you about today, I'm a theoretical plasma physicist who has learned astrophysics and space science by osmosis. I was a graduate student at Princeton before I became a faculty member, and there the culture thrives, going back to the peerless Lyman Spitzer, who established both the Department of Astrophysical Sciences and the Princeton Princeton Plasma Physics Laboratory, and who gave the first important idea in fusion, that was in fusion through stellarators, which continues to be a fantastic revolutionary idea for fusion physics that I continue to be very excited in pursuing. That's my other life, and as James said, there's much to be learned in straddling, and I really hope that what I have been lucky to do, many of you would have the good fortune to do as well. Moving on. Okay. The work that I present is the work of many good people. I almost feel myself parasitic at times, taking collective credit for all these wonderful people, and they're so many of them, including some present ones that I won't be able to thank individually, but have made striking contributions to this subject. As James mentioned, I was fortunate to have been given the James Clerk Maxwell Prize in Plasma Physics, and many of my predecessors and my teachers, including Spitzer and Rosenbluth and others, are people who were initial winners of that award. I was very fortunate to be in that group. So it made me go back and read about James Clerk Maxwell, and the more I read about him, the more I admired. He was very different from me, a deeply religious person, and truly a saint. And in every of those ways, he was very different. But somewhere in his very earnest assertions, there was this line: I have the capacity of being more wicked than any example that man could set me. And that, I finally felt, was the ground where I was, because I'm wicked by nature, a little bit, always trying to find things. And I identified immensely with him when he said that. And so I say, every time I give a talk, I like to quote him: please forgive the acts of omission and commission. I'm not acknowledging everybody who has made great contributions to the field. It's my apologies for that. But other than his very elegant equations, I think Maxwell was a marvelous example that we could bear to imitate even today, regarding his utmost dedication to physics and single-mindedness. The outline of my talk, I'd really begin at the beginning, not assuming anybody is an expert here. What is magnetic reconnection, a classic theory, the Sweet-Parker theory, why the plasmoid instability, which is a much more recent idea. It's amazing it went undiscovered for such a long time, and I think high-performance computing was critical to learning. So for those of us who are very trained in analytical theory, this is a good lesson to keep in mind. Do your asymptotics, but check it with good simulations, because if you don't, can get off the wrong path, even though mathematical analysis is so important. Some experimental evidence in laboratory plasmas, how the instability actually mediates turbulence, or can mediate turbulence. James's work in this area has also shown well that instability can be subdominant, and it is not something that I'll have the chance to do. Oh, this bar, I'm just going to make this full screen. Okay. Thank you, James. Planetary magnetospheres and extreme space weather events are some examples. I mean, the sun and the heliosphere is one place because of spacecraft. You have in situ data on magnetic fields, something that astrophysicists never had the luxury of having. And that, in fact, does constrain theories. On the other hand, it's a restricted environment in many ways from the plasma regime point of view, because astrophysics is so much richer in possibilities. But still, the ground truth through laboratory and space can be good checkpoints for theory that you want to apply ambitiously to astrophysical environments. And I'll mention a few of these as I go along as well. Talk about 3D magnetic reconnection if time permits, and some summary and open problems. Magnetic reconnection, a working definition. What I mean by magnetic reconnection are those that are brought about by departures from ideal behavior. So for those of you who know the elementary equations of Newtonian MHD, know that the ideal Ohm's law has E plus V plus V equals 0. What is different in non-ideal MHD is that you have an R on the right-hand side, which is as yet unspecified. In fact, there's something called a generalized Ohm's law, which has all kinds of terms on the right-hand side. But we will approach this problem from a general point of view, where the only requirement that we will make is that E dot curl cross R is not equal to 0. That turns out to be a definition of reconnection. An example is resistive MHD, where this term can become eta J, curl cross R becomes eta del square B, and when you dot it with this, you just pick out the parallel current, and that is not 0. So no wonder when you have resistivity in it, you break field lines. but so can other terms which have a very similar property. And this allows field lines to reconnect. And as I mentioned, it can include Hall current, electron inertia, and pressure tensor. All of these things are important in both collisional and collisionless systems. Take your pick. But if you have flat loop braking, you will have a connection. The classical theory in this was first thought about by Sweet, actually, and Parker wrote a paper laying out the proof for what he called Sweet's theory of reconnection. For those of you who haven't had the privilege of knowing him, he was a very strong exponent of his own ideas, but he was very generous to his colleagues. And so eventually this came to be known as the Sweet-Parker theory of reconnection, because his paper, presented in a symposium, appeared before Sweet's unpublished report, which motivated his work. But what they were looking at was a special kind of magnetic field topology, where the magnetic field points in opposite directions, and there is an in-between line called the so-called neutral line where the magnetic field vanishes. What they were looking at was collisional, resistive MHD description, incompressible, and assuming that somehow due to some miraculous external forcing that you may or may not have in many contexts, but they were looking at the sun, and this seemed like a reasonable set of assumptions that you gently push them so that you have delta T equal to 0. And they showed from simple conservation laws that when these things happen, the magnetic field lines annihilate each other, a process called merging or reconnection, where the width of the current sheet is going to be L divided by S to the half, where S is the Lundquist number, defined as such, LVA by eta. Now if you look at that dependency, you see right away that the merging speed goes like eta to the half, not eta. It's a fractional power of eta. Because if that fractional power is 1, then you have resistive diffusion. And Parker had already known that if you want to understand things like solar flares, that S was much too long, much too high to give an interesting time scale. So what he was after was a process that would be faster than resistive diffusion, and this is what he came up with, which for the solar corona that he and Sweet were both trying to emphasize was still much too long. L over VA was 1 second, that's ideal, very rapid, but that's not the reconnection time scale. The reconnection time scale scales like eta to the half. So when you calculate with Parker, you get 10 to the power 6 seconds, which is still nearly a year, or a little less than that. Still a lot faster, longer than the 100 to 1,000 seconds that was observed for the solar flare timescales. So Sweet-Parker theory was unable to explain it. And so even though a very successful theory, in the sense that it was supported by high-resolution numerical simulations which vindicated the scaling law, and I know many of you have checked this theory out, so you know in your own simulations it works, but it didn't work for flares. This in fact led to a big set of questions in reconnection theory. Well, Sweet-Parker theory is right, but inapplicable. How do we extend Sweet-Parker theory? And so the people eventually came to a point where they said, no matter how accurately you do resistive MHD, you're not going to be able to get this time scale out of resistive MHD. You need to go to collisionless effects. People went back to reconnection theory. I was one of them. The Hall current, pressure tensor, bring in pick, how to get the reconnection rate higher up, and we felt that there was no solution to be found in the realm of resistive theory. Well, I was dead wrong. And so were many people who were doing this, because they missed a valuable thing. That even within the realm of resistive MHD theory, there was a way to get a reconnection rate that would not be too sensitive on S. And it didn't even require turbulence. It required just an instability that was there in a high Lundquist number system that we had overlooked. Okay, so here is a high resolution simulation. In 2009, when Yimin Wang, who was a person I learned more about plasmoid theory than just about anybody else, and he was my postdoctoral colleague. And even though I was the discoverer of the instability, the nonlinear variant of it, Mrs. Lehman's beautiful simulations where you actually see that the current sheet is an extended current sheet, but you saw it was an extended current sheet and then quickly broke up into plasmoids. Therefore, the Sweet-Parker state was a transient state that showed up only if the Lundquist number was small enough. And what was that threshold number? It was below 1 million. If you ran your simulations at 10 to the power 5, 10 to the power 4, you saw the Sweet-Parker current sheet still be there. But if you cross this, what you would actually find is this plasmoid instability, and this is what was discussed in the 2009 paper, and the nonlinear simulation is the one that I'm actually focusing on. But there's a linear instability theory underlying too. Chris always begins there, no matter what Thierry modes he does. And so I'll tell you how to get the linear growth rate out of this. But there's a linear growth rate and a nonlinear growth rate. And the linear growth rate, it turns out, the person who first told me about the linear instability was Nuno Loureiro at MIT, who was a graduate student at the time. And he came and he was having dinner with me in Maryland, and he said, I found that instability faster than what Rosenbluth found, or Brunner-Koppy found. I didn't believe it, because I thought I really knew the resistive instability inside out. I knew the dispersion relation, and all that I knew about was instability that grows like 8 to the minus 3/5 or 8 to the minus 1/3. But this guy is coming and telling me that he has an instability that is actually super unflaming. So why did I not find this? Or before me, I learned it from Rosenbluth. Why didn't Rosenbluth find it? He was flawless in his algebra. Well, this is the Rosenbluth-Koppy dispersion relation. And that evening I sat down and realized that, I'm sorry, don't let me get you in the details of it. This is the dispersion relation. All that I want to tell you, I realized what was really important in Loureiro's theory, but Rosenbluth did not consider, which was that he started with a Harris sheet that was Y. And he didn't ask, there was no reason for him to. He was applying to laboratory plasmas, where he had a diffuse current sheet. So he had this tan hyperbolic smooth current sheet that many of you start your simulation with. But as that current sheet becomes thinner and thinner, and its width becomes dependent on the Lundquist number in a way that was not in the theory, but you could go to his dispersion relation and rescale his equation, replace the width that he had with the Sweet-Parker width, and in 5 lines, I have the same growth rate as Loureiro. The reason of my disbelief was that Loureiro had his own independent analysis. And I said, but it must come out of the classical dispersion relation. Why didn't it come out? And what I missed was a simple thing. Replace the width that was done, the A in Rosenbluth, by L to the S half. Well, the boundary layer becomes dependent on resistivity in a complicated way, so you have to go through the scaling and you will get this result. Well, guess what? Loureiro did this in 2007. He got awards in APS based on his linear discovery. I showed how to get his growth rate from the Furtkelin-Rosenbluth dispersion relation, or the Koppy dispersion relation. Luca Commisso, who was my postdoctoral fellow, pointed out to me that Tajima and Shibata in the Plasma Astrophysics textbook of 1997 had a problem set in which the growth rate was written down. There is no mention of this instability anywhere but the problem set. I searched so much for plasma physics. You know, everybody has something important to contribute if you know only where to look. In this case, the truth was buried in a problem set. So really, they knew about it. But why didn't they use it? 1997, we were finding this, and Shibata was a very expert simulationist. Why didn't he follow through on this and publish our reconnection rate? But the really important thing was, this result, if you have a virulent tearing instability, it can saturate nervously. But no, this one didn't. And this was why I claim some credit for making the Loureiro instability more famous, is because it had a consequence. And this Loureiro did not point out. is that you start off with a linear instability. That non-linearly below a Lundquist number, 10 to the power 4 gave you Sweet-Parker scale. But if you exceed 10 to the power 4, the scaling started deviating. And you get a reconnection rate which is 0.01 VA, independent of the value of the resistivity, as long as the Lundquist number was over 10,000. And therefore, our claim that resistive MHT theory was dead was wrong in the first place. Because resistive MHT can give you nonlinearly a reconnection rate that's independent of resistivity. And people who are doing turbulence simulations at inadequate resolution, there was always this cloud around that. They were claiming turbulence can give you this. No, the plasmoid instability, well resolved to run at high Lundquist numbers, can give you this reconnection rate. But remember, the answer is 0.01 VA. That's still an order of magnitude less than what we needed to be in order to understand solar flares, which is at 0.1 VA. So resistive MHD carries you part of the way through, but you're still off by a factor of 10. And we'll have to return to this later on, and it turns out that non-ideal mechanisms of the kind that we were talking about turned out to be pivotal in raising the reconnection rate from 0.01 to 0.1. But it wasn't from Sweet-Parker to there directly. You went through the plasmoid instability, and then collision-less effects elevated that reconnection further, and I'll get to that. I mentioned this point because this is a point of contention between a paper which is very popular in the astrophysics community, which I still disagree with respectfully, a paper by Lazarin and Vishniak, which claims that you can get to 0.1 purely from resistive MHD alone. I have not found this result to be true. Even with plasmoids, you are short by a factor of 10. And there is actually something even more subtle going on, because when Lorero or we, and this was first pointed out by work done by in the solar wind community by Marcovelli and others. I want to give them credit first, because Marcovelli and others actually said, you know, do you really have to wait to get to Sweet-Parker? Can't you go unstable to plasmoid even before you get to Sweet-Parker? And the answer is yes. Because as the current sheet is thinning, you don't have to wait to get to the Sweet-Parker model. In fact, this study showed that mathematically you treat the problem differently, because the gamma changes as a function of k and time. So you do a WKB ansatz and go through this analysis, but you actually find when you do this problem that you actually get, even before you get to Sweet-Parker, the plasmoid and gamma tau A of the order 1 and 10, you have very rapid growth in the instability. If you look at the width of the current sheet, it hasn't quite gotten to Sweet-Parker yet. It's some fractional power of eta, but not quite half. The system doesn't wait for you to go to unstable at eta equals half. It spontaneously is unstable even before that. And by gamma tau A of the order 10, the current in the system is already disrupted, falling down. And so the plasmoid instability, and this is what I was saying, Pucci and Verli's work drew our attention. They didn't do the simulation. This was Wong's beautiful work again, where he actually demarcated exactly. And the paper Uzdensky and Lorero, they say that this actually occurs in gamma tau A of the order 1. That's not quite right. It's of the order 10. You know, I care about factors of 10 because we are a factor of 10 short in the reconnection rate, and I can't just fudge that and say we can just get there. So these factors of 10 matter when you get there. But we showed that asymptotically as well, and so this goes to the solar wind community. Pucci and Veli and Narani and others drew our attention to this, and we redid the problem. So basically, it's still the nonlinear plasmoid instability, and I want to show this is just not a resistive MHD phenomenon. Suppose you have a Hall MHD, where the generalized onslaught doesn't only have eta j, it plus has j cross b. Or if you have a pink code, where the pressure is a tensor, the curl of gradient pressure is 0. So that does not contribute to reconnection, but if the pressure is a tensor, as it is most of the time in pink codes, because the distribution function is non-Maxwellian, you will get reconnection going in these codes. Plasmoid instability can occur in both resistive Hall, done again by Huang, in this very large, the largest Hall MHD simulations, this is all 2D, don't even need 3D. What you see is, first, the plasmoid instability resistive, and then Hall kicks in and it has a tendency to push out the plasmoids out of the problem and give you X points, which then again goes unstable to secondary instabilities, and the system goes back and forth between the three. The reconnection rises to 0.1. Or you go to Norton's full repeat simulations, he has a collision operator on the right hand side, but it's fully kinetic, and it shows plasmoids, and the reconnection rate is 0.1. Numerical simulations, therefore, multiple numbers, and make a compelling case that through the plasmoid instability, be it the collisional or the collisionless regime, you're going to get to a regime independent of the lumpness of the resistivity. Second, if you don't have collisionless effects, you will stabilize at 0.01 VA, which is not high enough for many eruptive events. If you want to understand then why it is 0.1, you have to invoke some collisionless effects. Inevitably, what is happening in these problems is that kinetic effects are important. In fact, in some cases, resistivity is so low as to be unimportant, in which case you must have things like electron inertia, things like the Hall current, things like the pressure tensor kicking in and giving you much rather. And that is probably closer to the real astrophysical plasmas than it is within the scope of our codes. We are very reliant on MHD codes still in the astrophysics community, but watch out, because they're already found to be wanting in those environments where we've actually measured current sheets and widths.
Well, but isn't the process that's thinning out the current sheet, which really is an essential piece of
the outer region
process you're describing,
Yeah.
a significant part of the domain of it.
You're absolutely right. To the extent that the outer region is concerned, yes, I believe. But the question is the inner region physics match for the outer region? Is that the balanced picture, or do you want to take the perspective that, inner region will somehow adjust itself to give me the number that nature finds, and that's microphysics. And I don't want to fall into the latter thing, because what I find is that when I actually do an asymptotic analysis matching the outer region where MHD is very, very good, it's an amazingly great model, and I match it to the inner region, the answer I get does depend on the matching and what I'm getting. Though, the plasmoid instability, you could say, look, with the matching you get 0.01 VA. Yeah, you're right. So even if it doesn't depend on the value of resistivity, but I carefully take into account the presence of resistivity and cancels out, I can actually show that. That is pleasing to me. Where I can show it, I am happy. When I cannot, I'm nervous about killing it. I want to quickly go through saying, what we are talking about is the subject of laboratory plasma experiments. FLARE is coming online in PPPL. Hantao G is a dear friend, and he's going to produce results. But and actually, the plasmoid instability, what Hantao did with Dalton was to write out a phase diagram plot for reconnection, pointing out where the plasmoid instability could be important. And this is where single excline collisional is where Parker theory is good. But as you move to collisionless domains, including Hall or importance, many of these systems are amenable to that. And what we need to do is to figure out that the phase diagram for reconnection now has multiple possibilities, and the collisionless regime. And many of these cases, you will get the magical number, but provided your code has those numbers. Now, a piece of magic would be if you could fix the resistivity in your code to raise it to the reconnection rate you want. Unless you can give a good physics argument why that is so, be wary of that. Because this is what we did in the good old times. When we didn't get the answer we want, we raised the resistivity till we got the reconnection rate we wanted. This is no fix for the problem. I've learned through experience that that's a wrong way to do physics. Yeah, you can get observational signatures, but you have no theoretical foundation. Unless you can find a kinetic instability that happens to produce the right amount of resistivity at the right place, be careful.
Yeah.
What does hybrid mean here?
Okay, so it's really good. What they're talking about is this is where whole terms become very important. Here you're getting the plasmoid multiple X line, so many plasmoids. When you move to the more and more collisionless regime, whole terms are kicking in. And remember, there was a tendency for the whole terms to explode plasmoids. So you got plasmoids, but not as many. Call that the hybrid. Here, when you've completely switched off your collision operator, every bit of reconnection is occurring between electron inertia and pressure tensor. This is some analytical results in the electron inertia case. That's a very special case. It's called Hamiltonian connection because the inertia term is actually time reversible. And that's a very interesting property. It's reversible. You change t to minus t, there's a possibility of unconnecting. But that never happens in real life because there's always some real dissipation that stops it. But in principle, it is possible. But the pressure tensor is often there, which actually gives you a condition. So and these are the initial results from flare that's beginning to straddle, but let's hope that flare will go a lot beyond. The Madison Whipple facility, I know Ellen Zweigel was visiting, and in her own home institution, there is a connection experiment called TREX, which is actually beginning to see plasmoids and their gradual evolution. This is just to say that for the laboratory plasma physicists, there's no excuse not to put theory to the test. They can measure everything, magnetic fields. They're not, the boundary conditions are often different and it's not directly applicable to astrophysical systems, nor are they collisionless enough, but they can check the theory, and the theory has been so far checked out. Now, the question is what happens to the plasmoid instability? As you go from 2 dimensions to 3. Now, imagine you had this Harris sheet, and I was showing you dominantly in 2-dimensional result. If you extend it in the 3rd direction, there's still an oblique tearing mode that was worked out by Scott Barrow and worked out all the growth rates and everything. I won't dwell on that. We always check linear theory carefully because it's a check of fidelity of our codes. And 2, are we getting, or is the theory wrong or not? So asymptotics has to be tested by scaling. Now, all of that has been done. We go to the nonlinear evolution now. And what you have is in 2 dimensions, you imagine you extend it in the 3rd direction. So the plasmoids, if they have no variation in the 3rd direction, would still be this sharp-edged plasma. But when you extend them in the 3rd direction, they become flux tubes, the magnetic fields line that are sharing. And imagine you actually have these plasmoids. It's a little bit like Jackson Pollock's painting, you know, those painting things and things come out. This reminds me very much of a Jackson Pollock painting. So when you actually do this, you gradually find flux tubes grow, they expand in size, and they start overlapping. At which point the magnetic field lines are not lying on nice tubes or surfaces anymore. They're becoming what you call ergodic or stochastic, and with much more diffuse structures. This system has a strong field in this direction, so that's the reason why its flux tubes are mobilizing. But if you look at the projection, the plasmoids will be much more blurry. Newman ran these at sufficiently high resolution that he was able to quantify how much energy was kinetic, how much was magnetic. But by this stage, you started out with tearing modes that were plasmoid-like, and the flux tube has made the turbulence very broad-based. And if you look at the slice, the 2-dimensional slice, you still see blurry plasmoid projections on this plane, but if you look at the 3rd dimension, it's also quite turbulent. And you know, in James's simulations, it's one of the world's largest MHD simulations. You can look at his things. He has tons of these flux tubes. 10,000 cube gives you a lot of room to resolve everything. And you will see structures like this. But you also see flux tubes and stuff like that. I'll mention James's work later on because I'm going to lead you up the garden path and telling you what happens in turbulence that is driven by plasmoids. And then he did an example where plasmoids become peripheral. Something else is happening that's very exciting and interesting. But we'll get to that in a moment. So if you look at the slice, it looks like somewhat like an expanded 3-particle current shape, but with turbulence in it. So if you look at the turbulence energy or the reconnection rates, first you say reconnection rate. When the system goes 3D unstable, it's no longer possible to define a flux function. For the plasmoid instability, if you have translation symmetry, then you have a flux function, and those surfaces give you nice K-M surfaces, Kolmogorov-Arnold Moses surfaces. But if you break the symmetry, you destroy flat surfaces. So how do you define then reconnection in a three-dimensional system, since you can't define a flux function? Well, what we did in this case was that we did what is called a mean field theory, which is that we took a mean magnetic field by averaging along the third direction. And that direction is an ignorable coordinate in the problem. We calculated the flux function for that, and when I'm plotting the reconnected flux, that's the mean flux rate that I'm computing. If you look at it, 3D sweep Parker, 3D plasmoids, the lines aren't a whole lot different, and the reconnection rate, if you look at it, they're comparable. So there's not a whole lot of difference, even though the morphology of the magnetic field, or the structure has changed profoundly. The average reconnection rate is still veering around 0.01 VA. So no matter how you define it, reconnection rate is not a sensitive measure necessarily of the nature of turbulence that goes into 3D systems. These are all sort of chewing up mean flux at about the same rate. Something that surprised us a bit. But if you look at the outflow comparisons, you actually find that the Sweet-Parker flow is much more localized along this, and there's a broadening of the flow channel in the turbulations, 3D. And this is actually one that does play a role because you have more of a channel through which you're pushing the flow out, so that does help it somewhat. If you look at the energy fluctuations, it doesn't fit a standard phenomenology. In fact, in Wong tried to quantify alpha. It's not Goldreich freedom, it's not Hiroshima correction. None of these things, we resolved it, and it turned out that the numbers were something like KT minus 2.2. And that's the first time we ran into 2.2, and we knew that something is going on in the dissipation rate, the dissipation part of the spectrum, which is different than what our standard theories have. And this is the first time we encountered the so-called 2.2 scaling law. And in an effort to resolve this, we knew that we'd have to do a simulation that is much larger. So Chuan-Fei Dong, who was my postdoctoral colleague at the time, a Jackie fellow, he took code and did a 5,000 cube simulations. Now this is dwarfed by James's 10,000 cube, but even as recently as Chuan-Fei's work was published, what he did was he actually went and did a simulation where he could resolve the inertial range as well as the dissipation range. And by that time, when Ewan's work was published, we knew that there was a new scaling. There was work coming out. Turns out that Carboon, 1990 in the solar wind community, thought something was going on with this stuff. He was very interested in turbulence and not the plasmoid instability, but if you look at his curves, he was finding deviations, and he got the closest to 2.2, though he didn't make a big deal about it, but it's there in his paper. Loureiro, and more convincingly, Borger and Loureiro 2017 wrote a paper. My favorite paper is the one by Luca Camiso. I'm biased. Luca worked out the scaling law as well as the logarithmic corrections. He's the only person who did that correctly. What he said, what the original scaling law is Borger and Loureiro, is that you actually, in the turbulence, you should have the induction of fraction and anisotropic spectrum. As you may know, Goldreich that gives you K-pop to minus vectors. I should keep much of the time.
We're good. We've still got 15 minutes.
Okay. I have to skip something. K-pop to minus 5/3, and what we found was not K-pop to minus 5/3, it was minus 3/2, and this is a long story. It has to do with the so-called phenomenon of scale-dependent alignment that Border introduced in order to tell people when Goldreich is not valid. Goldreich, in his typical deeply insightful fashion, did the numerical work, didn't find his scaling law, and wrote in his paper, I'm not finding 5/3, but I'm finding 3/2, but I'm finding 3/2 because of intermittency conversions. And he left it at that. That was Merriman Goldreich. And then more work happened, and 3/2 scaling law seems to be happening in many of the simulations, but there was a controversy in the field. Is it 5/3 or is it 3/2? Baudelaire came and said scale-dependent alignment, and he said, no intermittency. Well, Baudelaire is wrong. Goldreich was right in the first place. What he did was a variant of intermittency. So Goldreich didn't go as far as to actually say that this was scale-dependent alignment, but 3/2 was a definite result, and he didn't fudge it in his simulations, even though his theory led him to 5/3. That was Jason Meron. What is the alpha? That was our, and this is Chuan-Fei's result. He did the simulation with 10,000 where there are no plasmoids, and then he did the simulation, and he's the only guy I know at the time, and now James has done this too, who was able to resolve with or without plasmoids and calculate scaling grounds. And it took him a year to run this on NASA's Pleiades mission, published in PRL 2018. And he came to the conclusion that at 10⁻⁶, you get 2.2, if not, go on a different curve. So the plasmoid instability, what is happening is the current sheet is thinning down, well before collisionless effects or anything like that take into effect. The plasmoid then decides where the dissipation range is, things go unstable, and you get a new scaling law 2.2. This was vindicated further by his three-dimensional simulation that was published in Science Advances. And so you have the stirring range, you have the 3/2 range, and then you have the 2.2 range, predicted by theory, including the log corrections. The theory is in very fine shape. Till James came around and messed it all up by saying, hey, you have plasmoids, but I get 1.8. And we still don't have an theoretical explanation. We are working on it. Hopefully we'll find it before he publishes his next paper, but he has a new scaling law, which I won't go into because it's going to take me away from the mainstream. But watch him and what we do next. What I want to do is to bring you up to some things that I heard even from some of you today regarding your experience in trying to understand what plasmoid do in terms of particle acceleration problem. And my inspiration for this actually came from my former postdoc, Mijin Chen, who did all this even before the plasmoid theories was around. What she did was she went to MMS data, a cluster data, prior to MMS, cluster data, the European spacecraft. And she was looking at the Earth's magnetotail. The Earth's magnetotail, and Shantanu was telling me about some of the geometries he's looking at now, and there's this dipolar field which has this custom structure. So he was looking at the magnetotail, but the solar wind has pressed the magnetic field so very, very much that it almost looks like a Harris sheet. The field lines pointing in opposite directions. And Lijan actually measured using cluster, and she used the diagnostics that is crossing this line, then you would see this dipolar signature in the Z field. And you have local magnetometers, which are actually finding this. So these were Lijan's observational findings. What she found was that she looked at all energy channels. And her striking discovery was that when she actually cataloged, looked at BZ, where BZ is 0, you have exponents. Where BZ is large, you have the O point of an island. What she found was the maximum number of particles were actually accelerated in the center of the island, which is an O point. Those were not the highest energies, but those were the maximum in number. Exponents are very localized. You get much higher acceleration there, but then many fewer. And this, I think, was a very important insight in solar physics, because we had in the numbers problem, I had talked with Anatoly Spitkovsky about this, and maybe you don't have enough measurements to pin this down, but in solar physics, there was a major crisis which was called the numbers problem. The numbers problem was, if you relied on reconnection, you could get the electric field and the energies. But the number of particles you actually energize are localized around exponents. And Resi measured how many particles were actually accelerated to higher energies. And the number of particles were much larger than what exponent acceleration could give. And this led to a sort of, I would say, an important shift of paradigms in the space community, because Drake and others came out and said, it's not just exponent, it's the contraction of the islands. This is why when you were presenting your results today, I was asking you, I'm looking at your densities and they're not at the center, Ligon's observations led us to believe that the friendly contraction of the island was playing a role. So you're getting acceleration both from the X points as well as the circularizing of the island, so to speak. Okay, I'm going to go on to, so that's one thing. These were substops in the Earth's magnetosphere, and beautiful observations in the Earth's magnetosphere on these problems. You see the auroral bulge, and this was taken by Louis Frank, who was one of my colleagues at Iowa, one of Van Allen's students. And he took the most spectacular images of the auroral bulge, what happens on the auroral surface. So typically when a substorm would occur, you get a sudden intense bulge, and what is the picture and how it is triggered? This is the picture that gradually happened, is that, just as I was telling you, Shantanu, the solar wind takes the Earth's dipole field and thins it down. So you have a solar wind drive. This is not there in neutron magnetospheres, but it's there for the solar wind. And what it is doing is thinning the magnetic field down, and you get reconnection going, okay? That's about 20 to 30 Earth radii. That reconnection then travels inward. Both flows, inward and outward. And eventually it actually causes a substorm onset at nearer distances. And look at how cusp-like the field lines are. But the major reconnection is actually occurring because of the antiparallel field lines a little way down from the cusp, and the flows are coming in. And my picture was that what is going on in these cases is that you have a ballooning instability, an ideal instability, pressure-driven and curvature-driven, that drives the tail unstable.
What roles are the fault flow lines here?
What it's doing is that it's carrying flux from the mid-tail distances in there.
Right.
And because of flux pilot and
Well, yes, but on small scales near the X point, is the flow having any additional effects on the process of reconnection?
it surely does, because in the vicinity it's actually causing chewing up of the flux. And on that, all the theorists and the observers agree. The critical issue was what triggered, so that's happening at 20 to 30 Earth radii. But the location of the onset of the substorm by observers spin down to be 10 Earth radii. The problem was at the 10 Earth radii, the perpendicular component of the dipole field is so strong that you can't tear the sheet. You know, like if you have antiparallel sheet, that's one thing. If you have a perpendicular component that makes the four dipolar, look at the topology. The field line is all pointing in the same direction. It's not reconnected unless you get that perpendicular component down to zero, and the field lines can become antiparallel. That is happening further down. What is happening nearer distances when you have a remnant dipolar field? I argued that it was an ideal instance, not reconnection. Reconnection starts the process. Sam Totarica in my group did the best simulations, but I'm very biased. I think my postdoctoral colleagues and students are the best things since sliced bread. So if you tell me waxing eloquent about them, take me with a grain of salt. I'm very enthusiastic about their work. No apologies needed. But I really believe that Sam did the best simulations, albeit with a mass ratio that was not large enough, but it was a three-dimensional simulation. And I actually show you the difference between 2D simulations and 3D simulations. And what you're looking at here is Sam doing a fully pitched simulation of the Earth's magnetic tail. The 2D simulation and the 3D simulation have somewhat different outcomes. In the 2D simulation, there is no variation perpendicular to the plane of the paper. You see the connection occurring, the current sheet will thin down, and you will find what is called a dipolarizing flux. Chris was asking what the flows are doing. They're bringing in flux from these regions inward, and they will do so here as well, except there is a difference. Look here, you will find that this piles up, and the current density gets stronger and stronger. And you eventually get reconnection happening purely in 2D, but what really happens in the 3D simulations is that you get a disruption of this front, called the dipolarization front, that must be due to a mode which has undulations in the plane perpendicular to the paper. I was able to show theoretically that that's actually a pressure-driven instability. So what is happening in this problem is that you're driving the system, a thin current sheet forms, reconnection is setting it up by forming the X line, driving the flow inwards, which then goes unstable to the ballooning instability. And when I look at some of Bart's beautiful pictures on this, he knows that I keep pushing this thing about that there is an ideal instability that is disrupting the current sheet. Otherwise, I can't make sense of it purely on the basis of the connection alone.
Well, this has been an issue with magnetar flares.
Yeah.
In magnetar outbursts, you certainly produce a dense quasi-thermal paraplasma. You see this X-ray burst.
Right.
And so, the simulations that have been done of twisting anti-magnetic field, of course, they produce ideal resistant instabilities, but they don't have the photon pressure. And so it's been an outstanding question, because the dipole pressure is dropping off so rapidly, do you actually get some ballooning type effects?
Exactly, and I'm actually saying that's what is going on, and there's this kinetic ballooning. And why you need kinetic effects more than MHT is because MHT gives you data which is much too optimistic for instability because it doesn't include finite radius stabilization. When you include that to kinetic theory, and you can mock that in fluid theory by putting in additional correction terms that you derive from the kinetic theory, and you will see this effect. But the fluid theory does capture a lot of the essential physics. And this is what Sam would say is the disruption of the current front. So this is the current front that is coming. This was observed, by the way, by Pence. So this is now on very... The substorm community still argues whether it is reconnection that drives the onset. And in my mind, I don't have an extra drawing here. Reconnection starts the whole process. But ballooning is the one in my mind, at least I see in Sam's simulation, that breaks the question.
Well, but okay, this process as it happens in yours, what time scale are you talking about?
I'm talking about 1 to 10 seconds.
Okay. So you need multiple spacecraft for this.
And the cluster have 4 and MMS has 4, and they are very... so without multi-spacecraft measurements, how are you going to get this done? You have to see a front traveling, and the spacecraft pick that up.
Probably about 2 minutes.
Okay. They have energization. I have some wonderful stories that, like, you're trying to reproduce this non-thermal particle simulation. So this is coming out of PIC. The power laws you get power laws and stuff like that. And if you want to do it by MHT, that's why I'm so keen on understanding how your resistive model is actually producing that. That's the heart of the picture here. I would say it's impossible to get this right by just fooling around with the resistivity, but I don't know enough about relativistic plasmas. This is all Newtonian simulation, so I look forward to learning.
Newtonian, I do think it's impossible, but in relativistic there's a way around.
Yeah.
Show it in the blackboard.
Okay, I look forward to learning. So, by the way, what we get out of these PIC simulations eventually agrees with observations and all that. This is why I think Sam did it. Saturn, Jupiter are similar, but not these measurements. These are Earth measurements, but many of the timescales, they make sense. Even Kepler produce some of the timescales and some of these observations, and we have done enough modeling, I don't want to get into that. This is actually Mercury space weather event. Mercury has a gigantic plasmoid that it erupts. So I'm giving you confidence that if you want to do magnetospheres or neutron stars or pulsars or whatever, there's something to learn in what has been done, but you need to transfer this all to the relativistic domain. I understand also your plasmas are often pair plasmas, in which Hall current is not an effect, because there's an exact cancellation, but the pressure tensor might be still a very important effect. The question is, how are you going to get the MHT to show that? And my goal would be to get kinetic effects in there somehow, and that's the program. The Jekyll is the multi-fluid code, which tries to get kinetic physics to more sophisticated closure relations that mimic kinetic effects. And we've done a lot of work in that area. I'm going to stop. I just want to tell you that Partfrey did this for the GR PIC runs, and this reminds me a lot of something I saw in Venice. It's hard not to be inspired by what is coming out of the astrophysics community. Fingers of God, and I'm no believer, So you know what? I'm going to stop because what I was about to get into are some of the aspects of 3D line tide fields, which I also know is of great interest to you, but it's not something I had the time to get into. I clearly bit on more than I could choose. So my open questions, comments are cutting sheets in 2D and 3D. which increase without bound in the limit of zero dissipation, and the plasmoid instability play a pivotal role in mediating fast reconnection. I hope I've convinced you of that. And I think it's important to resolve the current shifts. If you don't, then you can't really get this problem. The plasmoid instability in a high Lopez number system is a universal feature of weakly collisional and collisionless plasmas. The problem of fast reconnection is solved. We know how to get to point 1 or 0.01. What is not solved, in my opinion, is the onset problem. And let me tell you why I worry. Because if the plasmoid instability has thrown a monkey's wrench in our understanding. Why? Because before we had the plasmoid instability, it was advancement of theory, but we had these collisional regimes, and we said you had sweep marker hanging around until the current shift thinned down till it became below and Hall effects and pressure gradient tests were becoming important, and then you kicked up the reconnection. That time was a long time. That was 30 minutes in the Earth's magnitude. That is the growth phase. And we said you need to build up the energy during that growth phase only to release it during the reconnection phase. Now imagine the plasmoid instability comes in. It doesn't allow you to store. As soon as the magnetic current sheet becomes thin, as soon as you trigger the plasmoid, you're on your way. But nature does not work like that. Nature often sits for hours without doing anything. And my point is, the reconnection theorists haven't accounted for why reconnection is a mechanism for releasing substorms until they've accounted for when reconnection does not occur, as much as they do when it does occur. Because that determines the onset problem. I cannot get my astrophysics friends to zero in on this. They're just too happy to get plasmoids and fast reconnection. But what about the growth phase? When the thing is not reconnecting? So I think that the onset problem is not solved. The fast reconnection problem is solved, but the onset problem is not solved. Well, this I don't need to persuade you. I'm sorry I told this. The problem of apportionment between ions and electrons, this is encouraging students. You have so much to do. We know how to reconnection occurs and all things, but how is the energy divided between ions and electrons? We don't have a very good theory or simulations yet that do this very well. Analytical theory. I am totally with my friend Chris here. Unless I can do things analytically, I don't believe anything I get. Be it through brittle algebra, but at least it should make sense. I should be able to anticipate what is about to come from simulations based on scaling laws. A lot of turbulence work that we do is like that. I like that work. I should be able to at least make sense of that rather than throw more scaling laws in your face and say, see, I found a new scaling law. What use is that if I don't say why you've got a different scaling law? And all of this has a very important role to play for the dynamo. Why is the universe magnetized? And what role does reconnection play? Because it does play a role. And how fast is it in collisionless system? The whole collisionless dynamo problem is wide open, in my view. Because most of what we understand about it is really the resistive dynamo problem, and that too is incomplete. Thank you for your attention.
We have maybe one quick question, then we'll close for discussion. Under others?
Well, I was about to ask you earlier in your talk, but where did the sweet marker layers come from? And then you nicely explained to us that nobody understands it.
Well, how do they?
Well, the Earth's magnetotail, it sounds like there's now a constraint.
Constraint, but you know, so MMS has measured it.
Yeah.
What it finds is that, and that as theory predicts, it finds that the current density has a different scale length than the J parallel scale length, and there's a scale separation. J parallel is on the scale length of the electron inertia, C over omega PE. But B parallel has a different scale length. And this layer is DI. And so Hall-Emerson simulations get that right. Pit simulations too get that right. And this is what throws a monkey's wrench into the anomalous resistivity picture in my view. In other words, if you just take E parallel by J parallel, you can define an eta. In this problem, if you define an eta, I remember having this discussion with Ross Abdul. Can I not understand this Like simply saying there's a spatially dependent resistivity. Yeah, but what is the physics of this spatially dependent resistivity? If E parallel and J parallel are in different scales. Electron-positron plasma is one place where J cross T cancels out, D and Di coalesces. There you can get away with the picture of an anomalous resistivity because the scale of E parallel and J parallel are identical, and you can say, aha, essentially the collision-less thing is just giving me a localized resistivity, but not this disparate scale. What works for the electron-positron plasma is not a good picture for electron-ion plasma. And that's why I'm so curious to learn about what Bart is doing, because
We're doing pairs.
huh?
We're doing pairs.
You're doing pairs. And you're really okay there. So but I still like to understand how much you're doing. Can I even do relativistically electron and ion?
It can be the whole term.
You do the whole term. So then your picture may not be all that different from mine.
But, okay, so in the case of a,
Should we have cookies and coffee discussion upstairs?
yeah, I guess.
Yeah, we should.
Okay.
Alright, let's keep the discussion going upstairs. Let's take some time.
Do you think there is a difference between the pure Newtonian compressible and incompressible?
You know, I think that will not give you a fundamental change of scaling. What will
But
give you
small.
small
Yeah.
changes. In the del dot V, you realize, right? If del dot V equals 0 was used by Swiss
Yeah.
Parker. What you need to do is to put in rho VV,
Yeah.
rho in rho out. That ratio of rho out by rho in that could be a factor of depending on
I'll
the
look for it, yeah.
3, 4, 5,
Yeah.
but it won't change the scaling law. But you should.
See, like,
Anyway,
so
well,
in
very
relative
thin is
which has to be by definition compressible. You can't go to infinite.
So you definitely see a higher reconnection rate due to compressibility effects alone.
Exactly, yeah, it goes from 0.1 to 0.03, 0.04.
True. And you know, it's there in one of Parker's papers, he generalized it, saying, how can I generalize? Because he was trying to speed up his reconnection rate, any help he could get. So he thought, maybe compressibility will save me. No, it just gives you a ratio of rho out over rho in front of the exponents.
Yeah.
And
Is it a square root?
no, it's actually just
That's
rho in.
linear? Because I just think it comes from VA, right?
Yeah, I see what you mean. Yeah, it comes over here. So I think it's just a multiplication.
This in its original